So let me, okay, so maybe I will start recording. Okay. So I will start recording where we stopped last time for the newcomers. Now, the thing we want to discuss today, is the law of large numbers for diffusions in an environment and some additive functionals. So, just to recall the notation, etc. We are in RD. We are dealing with a diffusion process that solves a certain SDE. So I will only write the SDE when we start from 0. There is a diffusive part. So you have some sigma times dWs. WS is very motion. Then there is first part in the drift with x lambda 0 s ds. And then there is another part. But the first part is reversible part. So sigma omega squared is some a omega, and b omega is 1/2 of the divergence of a omega. So that part would be the reversible part. And then we add a local drift of strength lambda, which is constant in some direction, E1. So the drift part is lambda a omega times E1 dt. Yes. Yes. Okay? And the question is, so the questions we want to answer are for the positive lambda. Okay, I'm always assuming that lambda is less than 1. And then what we want to do, so the aim is to prove a law of large numbers for this kind of object in the direction, well, in any direction, but so maybe the first thing we would like to prove is that we have a law of large numbers for x lambda, so study the limit of 1/t x lambda omega 0 at time t, and prove that this converges to something. And this something I will denote by L of lambda, because it depends on lambda. So in particular, if you make lambda equal to 0, then L is 0. And we want to prove that Q almost surely. So of course, I forgot all the assumptions and the notations. So maybe I should recall here. So, sorry? Q and P. And also P almost surely. But actually, yeah, you're right. In particular, Q almost surely, which is important. But P almost surely is also important. So the assumptions are there are 3 plus 1, so 4. And the first assumption is that coefficients are random with a certain law. So let me quickly write like this. Coefficients are random. And so they are defined on some probability space with a certain law Q. And we assume that Q is invariant under the space shift. So it's invariant under the action of RD and ergodic. Oh, so this Q is the same as this one. And then I have two other assumptions, so A2 and A3, and I think that A2 is uniform ellipticity. So we use the uniform ellipticity of A omega a number of times to get some estimates, a priori estimates on x lambda. And I'm also assuming that A omega is smooth. And this is because I want to make sense of the SDE. And then there is a fourth assumption. I will write it below. So the fourth assumption which we actually need in order to get this law of large numbers, is the fact that Q has finite range of correlation. Which I think I called R0, this finite range. So if you take the environment into you look at the environment in two distant locations, you see independent fields. And how distant these locations should be is at least R0. Now, under these assumptions, what we want to do is prove laws of large numbers. So the first one is just the one for the position of the diffusion. So that will be a first statement. But then there are two other statements, because we are also interested in what happens with additive functionals. So instead of looking at that, we will also be considering more general additive functionals of the form like this, 1 over t times the integral from 0 to t, f of omega lambda of s ds, and omega lambda is the environment seen from the particle. So omega lambda of dot, this is the environment seen from the diffusing particle, from x lambda, from the particle. And so we hope that this is going to converge to something. And this something, if there is a limit, then the limit will be denoted by nu lambda. And actually, there is a limit for a certain class of f. And we want this to hold pure motionally, in some sense with respect to p, which is not important. So it can be pure motionally, it can be in L1 of p. We don't actually care so much about that, but it's important that initially the environment is distributed according to or is sampled according to the law Q. So if there is a limit like this, then we are happy. And there are two classes of functions for which we can address this question. So in any case, what we will prove will be for a local function. So here, f is local. And then there are two choices. So the choice, which is number 1, is you choose a bounded function. So f is bounded. And then there is the choice 2, which is, which naturally arose in the discussion of the central limit theorem, when we choose for f not necessarily a function, but an element in h-1. In fact, h-1 infinity, and I recall that h-1, basically it means, so f is in h-1 infinity, means that f is of the form divergence of something, some big f, and the infinity here means that you can choose f bounded, so where f is in L infinity to the power n. So such functions, we call them, in the space of functions satisfying this, we call it h-1 infinity, and we care about proving this law of large numbers for these two classes of functions. And then what nu lambda is in case 1, nu lambda is an invariant measure for the process of the environment seen from the particle. So in particular, it's a probability measure on omega. And in case 2, then nu lambda will define some linear functional and continuous one. So this is a continuous linear functional. On the completion of this space of local functions which are in h-1 infinity, that we called h-1 tilde. So these are two different views on what a steady state should be. And the point of view number 1 is the first one you might think about, which is to construct an invariant measure for the environment seen from the particle. But actually, the point of view number 2 is a point of view which is natural if we have in mind that we want to get fluctuation-dissipation relations. Okay, so it's less classical, but somehow more natural. Okay. So this is the plan for today, to prove the free statements. There is this one, maybe this one first, and then to construct silly states in these two senses, on these two classes of functions. Is it clear? Questions? No? Okay, and now one word about the strategy we're going to use. So the strategy we use in order to prove that is based on the construction of regeneration times. So we will construct regeneration times. In order to construct regeneration times, maybe, so regeneration times are, in words, times for which we will split the trajectory of, say, x lambda into ID pieces, and once we can do that, provided we can prove some estimates on the regeneration times, then we will get laws of large numbers by just applying the simple law of large numbers for ID random variables. The construction of the regeneration times is on path space. So the first thing we do is we work on path space. So my path space is, well, actually path space is, here it's omega, which we keep, and across the space of continuous trajectories in RD or in RD plus 1. I mean, if we only look at the diffusion, then we take passes in RD, but if we want to include an additive function, then we have to increase the dimension by 1 anyway. And so I will use the notation on path space, and in particular, I use the notation P lambda to be the annealed law of, say, x lambda omega 0 dot on path space omega also. And okay, and so we want to define regeneration times. The notation for regeneration times will be tau 1. So we'll construct a sequence of times, tau 1 lambda, tau 2 lambda, etc. And if we think about only the first statement, the law of large numbers for x lambda, then these regeneration times will have this property that they split the trajectory into ID pieces. So in particular, under P lambda, we'll get that if you look at the increments. So now I'm writing x for the typical path on path space, and I look at the increments of x between two successive regeneration times. So x at time tau k plus 1 lambda minus x at time tau k lambda. I also need the times, so the increments, the difference between tau k plus 1 and tau k, and this will be ID. And if we include an additive functional, then we want similar property for the additive functional. So once you know that, if you know some bounds that things are integrable, then you get the law of large numbers. So that will imply the law of large numbers. So in that case, for the position. Okay. So this is the strategy, and as I briefly recalled last time, the This is a strategy which has a long history in the context of random walks in a random environment. So there are 2 or 3 things that we should do. That is, one thing I want to do is to recall how we construct these regeneration times, how we define them. So maybe the first thing I will do is to give a definition, and then we should, in particular, we want to have a definition of regeneration times for which we will have this property that these increments are independent. Okay? So that's the first task. Now, the definition I'm going to use, it's mimicked on construction of regeneration times in the case of random walks in a random environment, which is basically due to Snitman, I guess, but also Martin-Zerner, probably. One thing we have to do is to adapt this construction to the case of a diffusion process, which is slightly different. But actually, the main idea is already in this paper of Lian Chen. So that's one task. Then another thing we have to be a little bit careful about is that, first of all, the first thing to check is that regeneration times that we are going to define are finite, for instance, because otherwise we wouldn't get anything. But in fact, we need a little bit more because we need some bounds. So we'll have to be a little bit careful at some point about what is the tail of the law of the regeneration times we are constructing. And this is something we need in order to justify the law of large numbers, of course. But all these statements are written for fixed lambda. So there is one issue, which is to control the size of the regeneration times for a fixed lambda. And that issue is already addressed in these papers of Alain and Martin and also Lian Chen. And that's the second stack. But in fact, if we keep in mind that eventually we want to prove fluctuation-dissipation relations, and these are related to the behavior of nu lambda when lambda tends to 0, then we need more. And what we need is also a good control of the regeneration times, how they behave when lambda tends to 0. Okay? So we are going to do that step by step, but the definition of the regeneration time I'm going to give is the one for which we, in particular, have the nice estimates we want in terms of lambda. So if you would only care about proving the law of large numbers for a fixed lambda, then you could just copy the construction in Lian Chen. But if you want to have the right order of magnitude in terms of lambda, then the construction I'm going to give is the one that works. Okay. So let's go. Maybe. No. I wanted to recall one other thing, which is the lemma that we proved last time, which are the 2 lemmas which will allow us to get some bound on the regeneration times. So we proved 2 lemmata, 1 and 2, which express the fact that the diffusion does drift in the direction E1. Then there were 2 lemmas. And the first one says the following, that you look at the probability, and this P is quenched, this is for a fixed environment, that you eventually hit hyperplane to the left when E1 is the direction to the right. So this is the probability of hitting the hyperplane x dot E1 equals minus L. And we had a bound about that with some constants. So let me skip the constants. But if I skip the constant, this has an exponential decay in L, in fact in lambda L. And then there are constants here and there, but I'm not writing the constants. And so that's one lemma. And this is uniform. This is uniform. So the constants, which are not written, are uniform in terms of everything. That is omega. Well, okay, so first, maybe I should have written process starts from x. So it is uniform with respect to omega x. Also lambda and L if you put the right constants. And anyway, we will take lambda L to be large enough.
X is in around the origin?
No, yes. No, yes, sorry. X is such that it is at the origin. Yes. But then yeah, and besides, I should not. Okay, I should put an x zero here because it's x zero. Okay. Okay. So this is not as precise as it should be, I guess. I'm not going to be better with the second statement of the lemma, which is so that gives something about the harmonic measure, but then we need something about time. So we look at the probability that x lambda omega x zero. It's now the hyperplane in the other direction, so x dot t1 equals L after time t. So we want to prove that. So we are going to hit at a hyperplane, but we want to prove that this happens quickly enough. And then there is an exponential decay in t. So the bound we have, ignoring the constants, is something like exponential lambda L minus lambda squared t. What is relevant in these estimates is the way they depend on L, t, and lambda. And these bounds are correct. I mean, if you think a little bit about that, then this means that you have to scale space by a factor of 1 over lambda. You have to scale time by a factor of 1 over lambda squared. And we already saw that this is the right scale. Okay, so these are the tools that will be used in order to get bounds on regeneration times. Yeah. This is the first heating time of this hyperplane being larger than t. Thanks. Okay? So, what is the definition of regeneration times? So, the definition of regeneration times is this. Where is the camera? You can zoom. I have to justify that.
Your sample pass, the diffusion sample pass looks like that.
Yeah, that's contained in the lemma. Exactly. Yes. If you look carefully at this drawing, you see that I was just a little bit optimistic. So, maybe it doesn't quite look like that because it's difficult for me to draw a non-differentiable curve or something like this. So you should zoom a little bit, but not too much. Okay. Now, so before I try to reproduce my drawing, let me make some definition so approximate definition, construction of the regeneration times. So let's construct, let's say, the first regeneration time. Now, you try to construct the regeneration time with the property that the increments are independent. This is what is important. And there is some kind of algorithm to do it. So the algorithm has different steps. Step one. So the first step is you wait. So we're going to look at what happens in the direction E1. So we focus on what the drawing is about. Is it's supposed to be drawing of the trajectory of the diffusion in the direction E1. Okay. Now we are on path space, so actually we are looking at some trajectory. So we choose a trajectory X trajectory, and then we run the following algorithm, which will depend on mostly, but not only, on the behavior of what the trajectory does in direction E1. So first thing, you wait until X in the direction E1 has progressed by something or a certain length of order 1 over lambda, maybe a little bit more. Okay, so you wait until the trajectory I chose has progressed by a distance 2 over lambda in direction E1. So actually, you look at the first heating time of the hyperplane at distance 2 over lambda. That defines a certain time. The time at which this happens, I will denote by n. So okay, let's say with the lambda. Everything will depend on the lambda anyway. So then, second step. So now you do something a little bit magical. You toss a coin. I mean, you all have coins, right? We're all probabilists. From time to time, we like to toss a coin. So you toss a coin. And there are two possibilities. Either you get a success or a failure. So if it fails, then you go back to step 1. So when you go back to step 1, that is, you ask the same question. You wait until the trajectory has progressed by distance 2 over lambda with respect to your new starting position. So you shift the trajectory. So each time we will go back to a previous step, we will shift the trajectory and start from the new starting position, which is where we are at the moment we go back in the algorithm. Now, if you have a success, then you add, in terms of time, you add a time. I forgot something here. Okay, I will write after that. So you add time 1 over lambda square, and so you make a shift in time of value 1 over lambda square, and during that time you force the diffusion to make what I will call a deterministic jump of order of size 1 over lambda in the direction E1. And so, and during that time, and then you force the trajectory to make a jump. I call it deterministic. It's not completely deterministic, I will explain. A deterministic jump of size, which is almost 1 over lambda, in the direction E1. So, what I mean by deterministic means it doesn't depend on omega. It will still be random, in a certain sense, but it doesn't depend on the environment. So deterministic here means independent of omega with respect to the environment. So if your coin tossing is a success, you temporarily forget about the environment, and then you make a jump to the right, direction E1, of size 1 over lambda in time 1 over lambda squared. And then you proceed to step 3. So maybe I can start drawing. So the thing I had forgotten is that even if it fails, you still add an extra time 1 over lambda squared. So here I should have said you add time 1 over lambda squared. So you wait for a time 1 over lambda squared, and then you go back to step 1. So let's draw a trajectory and see what happens. So what I'm drawing is in that direction, I'm drawing x dot E1. So this is direction E1. And in that direction, down there, you will have time. So you start. Now we start from the origin, but we will start from any point. And then you look at the trajectory. So you have to wait until you get at a distance, you increase the distance by 2 over lambda. So you look at where is 2 over lambda. So that defines a hyperplane like this. And then you have your trajectory, and you just wait until you get to that point. So that is the time n lambda. Okay? Now, when you've done that, you toss your coin. And then you look at the outcome. So maybe here we toss a coin. I can use colors. So in colors, I will be the coin tossing. So I toss my coin here and say I get a failure here. So I wait time 1 over lambda square. So during time 1 over lambda square, the diffusion process does something. So this is time n lambda plus 1 over lambda square. And then I start again. So I start again, but this is my new initial position. So I measure a length 2 over lambda from that point. So here I'll have a distance 2 over lambda. Okay. Then this defines the hyperplane. And then I wait until I hit this hyperplane for the first time. And then that defines another time n lambda. And then I toss my coin. Now, let us say that this time, the result of the coin tossing is positive. So now I make this deterministic jump. This is size 1 over lambda. And then you get to some location here. In time 1 over lambda square. So here we get to that point at time n lambda plus 1 over lambda square. Okay. So this is the description of the first part of the algorithm. So far, that's where we are. Now, this creates, so first of all, if we have a success, we make that jump, and that new time, n lambda after the first success, plus 1 over lambda square, I will denote it by s lambda. So the first step defines the time n lambda, and the second step defines a time s lambda, which is n lambda plus 1 over lambda square after the first success. Okay? Now, I write it like that, but I mean, until we can go to step 3, we have to do the coin tossing a certain number of times. So, as in the picture, we don't generate only one random variable one time n lambda, but a sequence of them. So we should give them numbers. So n lambda 1 is the first time, is the time you get when you run step 1 for the first time, and then so here the first time was a failure, and then you have to repeat the operation, then you get this time n lambda 2, because your second attempt was a success, and then you define the random variable, the random time, s lambda 1. Okay? So these are sequences, right? Where we are generating sequences of random variables, sequences of times, which are stopping times. Okay? And now here comes the first step. So we are in that situation when we just performed this deterministic jump, and then we ask if in the future the trajectory is going to backtrack. Now ask if the trajectory. So once again, the trajectory means the trajectory at that moment. So the trajectory after this time s lambda k, whatever k is. So after time s lambda k. So once again, we shift the trajectory. Our starting time now is less lambda k, and then we ask if this trajectory is going to backtrack. By distance at least 1 over lambda. So, in a more formal way, let us introduce this time d, which is the backtracking time. So this is the first time you hit the hyperplane, which is a distance 1 over lambda in the negative direction. So this is the first hitting time of, so we only care in direction E1 of the process x dot E1. So this is the first hitting time for this process of the hyperplane at distance 1 over lambda, but in direction minus E1. Okay, so that's the definition. And so asking whether the trajectory is going to backtrack or not is asking whether d is finite or infinite. So two things can happen. If d is infinite, then you're done. Then you declare that the first regeneration time, to 1 lambda, is equal to that time, S lambda k where you are. So that is, you finish. The algorithm stops. Otherwise, so if D is finite, then you start. You restart the algorithm from step 1. Then go to step 1. So once again, you shift the trajectory and you start again. So let's complete the drawing. I need a little bit of space, probably. I mean, okay, it depends whether we are optimistic or pessimistic. So you have this trajectory until this time. Now, so we want to perform step 3. So we should ask, what is the value of D? And this is not in the drawing. We can arbitrarily decide, because it actually doesn't depend on what the trajectory did so far. It depends on what the trajectory is going to do. Now on the drawing I see that maybe I should adjust some constants, so maybe I put a 3 here or something like this to have a little bit of thing. Okay, so that depends on the future. The future is completely open, so we can decide. So do you want the trajectory to backtrack or not? You don't want the trajectory to backtrack. So the trajectory doesn't backtrack. So here D is infinite, and it's over. If it did backtrack, we would have a part of the trajectory going back, and then we would have to start again. So so that's one possibility. The trajectory doesn't backtrack. Then another possibility is that the trajectory does backtrack. So D is finite. And so you have this trajectory. So maybe the trajectory is going to move to the right, but then at some point it's going to move here. And let's say this distance is minus 1 over 3 lambda. And then you start again. So you start again, that is, you draw this line, you add distance 2 over lambda. And so you look at the trajectory until it reaches that point. And that's a new n lambda. So in that case, it would be n lambda 3. And then you keep going like that.
Do you restart from the farthest point of the trajectory, or?
Yeah. You mean in step 1?
Yeah, in step 1.
In step 1, yes.
And if you go back from the
Okay. So you wait until the trajectory has progressed by distance 2 lambda from its past maximum. This time. Yeah. So you actually do that like this. That is, so when you have backtracking, in fact, as the drawing shows, then what you do is you wait until you actually backtrack. So when D is finite, so you wait until time D. And before time D, the diffusion is going to do something, like maybe it will go further to the right, most probably it will. And then at some point it will backtrack. So this is time D. That is the time here, where you backtrack, but this is time D computed for the trajectory in yellow. Then you look, and then you go to step 1. So you look at the past maximum, which in the drawing is here. Then you wait until you bypass this path maximum by a length 2 over lambda. You have this time n lambda free. And then you repeat the whole procedure. That is, you make a coin tossing, and depending on the results, you start again, or you make this deterministic jump, and then you ask again if D is finite. Okay? So then, this way, you keep creating sequences of random variables. Hopefully, at some point, you stop. So, of course, it depends on the trajectory. But these lemmas I have to erase now, they will be used to prove that for almost all trajectories, the algorithm stops. So when it stops, then you have reached the first regeneration time to 1. Before that happens, you had to iterate a certain number of times the algorithm. So I will denote by k the number of iterations, in the sense that, anyway, what will happen is that the regeneration time, the first one, is going to be one of these S lambda k's. So this big K is random, and it will be the time for which the 1 lambda equals S lambda K. So this is actually the number of times you iterate this step 2 with a success. And that defines the first regeneration time. And to define the successive regeneration times, you just restart from the previous regeneration time. So that is, once you have achieved that first regeneration time here, for instance, then you restart the trajectory from here, and you just apply the same algorithm again. Okay? So tau 2 lambda is defined as tau 1 lambda for the trajectory. So the same algorithm for the trajectory from time to 1 lambda, etc. I mean, tau 3 lambda is the same, etc. So with my definition, the algorithm will stop after k iterations, and then I think I may need to look at the times S lambda k where k is larger than bk, and then these are defined to be infinite, just for the sake of defining things. This k is the smallest integer k, such that you run the algorithm k times. So S lambda k is finite. And from that time, so if you look at the backtracking time, but you make a time shift of S lambda k, so the trajectory after time S lambda k does not backtrack. So this backtracking time is infinite. Okay. Is it okay? Okay. So it's almost good. There is I skipped a few conditions, and also I'm not 100% sure about this 1/3 and this 2 over lambda and things like this, but you can adjust these things. So you may have to adjust a little bit for for what I'm going to say to be true. Anyway, so assuming that the algorithm stops at a certain time, so we have defined the first and the other regeneration times, then we can make some remarks. Like, if you look at the position at the regeneration time, it depends on a number of things. So, first of all, it depends on this, or let's say what you do when you do step 1 and step 2. That is, you run the random walk, then you make coin tossing, etc. So there is one part of this algorithm, steps 1 and 2, which defines these sequences of times n and s, and these are stopping times. So the position where you are at time t1 lambda, and actually also the value of t1 lambda, they depend on the trajectory of the diffusion process until that time. But since this arrow is a deterministic jump, it doesn't depend on the environment. The position at time t1 lambda actually depends on that position. And that depends on what the environment looks like in this part of space. Okay? Now, this is one thing to x to 1 lambda depends on. So it depends on the environment and the behavior of the trajectory. This is the environment. To the left of where the process is, and strictly to the left by 1 over lambda. That is the environment, so the sigma omega of y's, for point y, which in direction E1 is to the left of the current position by at least 1 over lambda. Okay? And that is as far as steps 1 and 2 are concerned. And then there is this, this d, so the position of the diffusion and also time. It also depends on the answer to that question whether d is finite or not. So it also depends on whether d is finite or not. So it depends on this, and also on whether d is infinite or not. And that depends on what the... So, I mean, you are here, and then you ask, am I going to backtrack by this amount? So that depends on... I mean, in order to answer that question, you need to know what the environment is in that part of space. Because if you know what the environment, because anyway, to decide whether d is finite or not, you only have to wait until time d. So if you backtrack, then you do something, which depends on what the environment looks like to the right of this point, and maybe also a little bit to the left. But once you've reached this hyperplane, then you know that d is finite. So it only depends on what the environment, in terms of the environment, it depends on the environment, sigma omega of y. But now for y's, such that y dot E1 is larger than the current position, minus 1 over 3 lambda. Okay? And these two parts of the environment, they are separated by a length R0, at least R0, if we choose lambda small enough. So I will assume that lambda is small enough so that I think maybe it should be 2/3 of 1 of lambda, but let us put 1/3 to be sure. It's larger than R0. Okay? So in such a way that these two parts of the environment, they are separated by a distance at least R0, so that we will get this decoupling. Okay?
What is the size of the neighborhood? I mean,
So the size of this neighborhood,
yeah.
this is the size 10 to the minus 5 over lambda.
Order 1 over lambda.
Order 1, yes, everything should be on the proper scale. Okay? So that's one remark from the construction. Another remark is that we are using coin tossing. So I mean, if we want to be precise, then we enlarged the probability space. So we enlarge the probability space to include the coin tossing. But this is, of course, not a true difficulty. I think in the paper, at the end, we had to deal with something like 4 or 5 probability spaces, realizations of the diffusion. But so we had to look for different tech fonts to distinguish between the different spaces. But that's not a very big issue. And also, an observation is that if you look at what you see after time to 1 lambda, then what you see is a trajectory of a diffusion process as before, except that now the process is conditioned on non-backtracking. So the law of the trajectory after time t1 is the same law as before. So, but with the conditioning. So the law after time, the law of the trajectory, like this. So let's say, so this is a shifted trajectory, but it's stronger than that. It's the law of the whole process, including the environment, is, let's say, this law, P lambda, the initial law, but conditioned on the fact that you don't backtrack. Okay. Now I see it's almost time for the break, but maybe before we make the break, do you have any question? Is it clear? I mean, at this point, the definition should be, let's say, more or less clear. And also the thing that should be clear from the definition, I mean, actually, it's not completely clear. There are a few things should be added, but
for example, the role of the process is just a conditional measure if you don't make second regeneration. Whenever you make a regeneration, you insert the artificial jump, therefore the role is different.
So I have, anyway, this trajectory starts, yeah, okay, so
Yeah, what is written is
I understand your question. That is, this trajectory starts after the deterministic jump. But then, when we will construct the other regeneration time, the next one, we will have another deterministic jump. But these deterministic jumps, we will do them in such a way that we don't destroy the law, that we keep the right law. So, okay, anyway, there is one thing that should be explained in the algorithm, which is what exactly it means, I mean, how we force the trajectory to make a deterministic jump. So this is maybe more or less clear, but I didn't quite tell you what happens when it fails. So when we fail, when the coin tossing fails, then we have to make sure that what we ask the trajectory to do is compatible with the law of x lambda. Okay, but I will come back to that point in a more precise way. So I should be a little bit, yeah, okay. So that's one thing which is indeed not clear and should be clarified. Okay? Any other question? So if we admit that there is a way to make this deterministic jump, then let me give you an exercise. So I should have added one more remark, but this is just for convenience. So for convenience, we put things on a discrete scale. There is we can modify a little bit the algorithm in such a way that in the construction, so we construct the time S lambda k so that lambda square S lambda k is always an integer. So you take, how do you say, integer parts. When you define S lambda k, it's defined this way, but then you modify it so that you take the closest integer. And then this adds a certain number of small conditions. But on the scale lambda square, we don't change the value of S lambda k. And for instance, here is a property, so an exercise. Just to play with the algorithm and with this property that this deterministic jump will operate some kind of decoupling. I mean, to explicitly use the fact that the position at the regeneration time, it depends on these two things, the environment to the left, the environment to the right. And the way it depends on these two things is kind of explicitly written in these two lines. So, for instance, here is one property that follows from this, which is the following thing. Take any process, any nice process. So let h of m be a sequence. You can assume bounded, not very important, such that h of m is measurable with respect to the filtration. So this is a canonical filtration at time, I guess, lambda square m, lambda square m. So this is the canonical filtration. And then you want to compute, so assuming things are finite, you want to compute the expectation with respect to p lambda of h at time lambda square times the regeneration time. And condition on the fact that d is infinite. So this is the kind of thing that we will see when we, because this conditioning is what we see after time to 1 lambda. Okay? So I claim that this is a simple expression. This is the sum over k of the expectation. I mean, clearly, this time tau 1 lambda is 1 sk. So we'll get h at time lambda square s lambda k for some k. Now you can easily imagine what I'm trying to do is write the proof that I'll get if, when evaluating this, I condition on the big K. Okay? And then, what should we put here? Something is missing. So here there should be something for the formula to be correct. So that's a training exercise to train on the definition. Okay? So now we make a break, and after the break, I should say a little bit of something to make this coin tossing and deterministic jump story more precise. And we still have to check that regeneration times are finite for almost all trajectories with respect to p lambda. And in fact, we will need much more than just finiteness. But finiteness, we will need also some bounds. Okay? So we make a short break. So don't say anything. Nice one. So let's resume. Now, so the coin tossing. So let us be a little bit more explicit about this coin tossing procedure. So in the algorithm, at some point you toss a coin. So say at that moment you are in a certain location. So so we look at what happens at a moment we toss the coin. Let's call it Y. And so say we are at location X. So you have two possibilities. Either you get a success, y equals 1. This is a success. Then you make this deterministic jump. So the deterministic jump is that you sample the position. So we're at location X at some time, and time is t. So in the algorithm, you add a time interval of length 1 over lambda square. So you sample X at time t plus 1 over lambda square with the uniform law on that small ball over there. With uniform law on the ball, which is centered at point X plus 1 over lambda, and with this small radius, 10 to the minus 5 over lambda. Then you may have a failure. So you may have y equals 0. So this is a failure. And then you have to decide what to do. And what you should do, in words, is you have to do the only thing that you can possibly do in such a way that you catch up with the law of the diffusion in the random environment. So in other words, this behavior, jumping to the ball of radius x plus 1 over lambda, with this center and this radius, jumping to that ball with the uniform law is not what the diffusion in the random environment is supposed to do, because the diffusion in the random environment is supposed to have a behavior that does depend on the environment. And that doesn't. So you have to sample the value of x at time t plus 1 over lambda square in such a way that you retrieve what the law of x at this time is for good. And what does that mean? It means that what you will see after the coin tossing, this is a mixture of these two cases. So I need one more parameter, which is what is the probability of success or failure. So this I denote by delta. So let's call delta the probability that y equals 1. Okay? Then what I want is that if I look at the probability that I'm starting from point x, time is, so I start at time 0 now, and I am in a certain environment omega, so I look at x lambda omega, starting from x, sorry, the starting point is there, at time 1 over the square, and I look at the distribution of this, and I want this to be delta, so with probability delta, I have the uniform law, so delta times this uniform law, so the uniform law on the ball, of center x plus 1 over lambda and radius 10 to the minus 5 over lambda plus 1 minus delta times, and here I put what I mean, this is a definition of the conditional law on the event y equals 0. So actually what I see here is I want the probability when I condition on y.
So when you say uniform law on ball, it is normalized, right?
It is normalized. Yeah, it's normalized. So here we see the probability of my process starting at point x. I'm okay, playing a little bit with at time 1 over lambda square is in the set condition on y equals 0. And this defines, this tells you how you should sample the position at time 1 over lambda square in case of failure. Because you want to solve that equation. Okay. So this you know, and this you know, and this you know. I mean, once you fix delta. Okay. And that answers your question, which is even after a second coin tossing, the law that we will see will still be the law of the diffusion in the random environment. It will still be p lambda.
So you wrote a conditional law because they are not independent? Or
What is not independent?
y and x. I thought they independent.
No, they're not. No, depending on the outcome, you sample x at time 1 over lambda square in different ways. The y does not depend on the past. It does not depend on what happened before time 0 in this expression. Okay? So when you toss the coin, you take the coin out of your pocket and then you toss it, and it's independent of the rest. But depending on the way, on the value of y, then you do different things to decide where the diffusion will be at time 1 over lambda square. Right. I enlarged the space.
Yeah.
And I didn't write everything, because in fact, what I should write is what you do after time 1 over lambda square, but then you run diffusion in the random environment.
And because of uniform relativity, you can choose delta uniformly.
Okay, then we have to discuss how we choose delta, and this will come from Aronson bound. But even before we do that, there is one thing that I'm not telling you, which is I'm telling you how to choose the position at time 1 over lambda square. But there is one thing I'm not telling you. I'm not telling you what the process does between time 0 and time 1 over lambda square. Okay? So we lose something. So as an observation, we lose the information on the trajectory between time 0 and time time 1 over lambda square. So that's not very important, because we don't lose any information about time, because the jump occurs in time exactly 1 over lambda square. And we don't lose the information about the position, because the position, at least, yeah, the position in case of a success, we know how it is sampled. But anyway, but still, if you wanted to track the whole evolution of the whole trajectory, then some information is lost in this definition. And indeed, there is this question about how to choose delta. So the condition on delta is the one that is written here. And so why is there, let's say, a fixed delta which does not depend on x and lambda that satisfies this equation? This is due to Aronson bounds. So
could you tell me again what do you mean by the last sentence?
Okay. So you have the trajectory of the diffusion. Then you stop at some moment where you do a coin tossing. Then you toss your coin. Suppose you get a success. Then what I'm telling you is then the diffusion at time 1 over lambda square, I'm telling you where it is. And how to construct the new position is forget about the environment. Just look at this ball at distance 1 over lambda, and then you sample a point uniformly with respect to that law. And this is the position at time 1 over lambda square. Now, what did the past do in between these two times? The time at which you toss the coin and the time, 1 over lambda square. Later, you don't know. I'm not telling you.
No.
I'm not telling you. Yeah. So this is not so important. I mean, okay. If you wanted to keep track of this, you would have to modify a little bit. If you only care about the positions of x at regeneration times, you don't care, because I'm telling you how to decide where the diffusion is at the regeneration time. And if you only care about time, then it's okay also, because you have computed S lambda, and then you just add, actually in the definition of S lambda, there is this plus 1 over lambda square.
Don't you have to make sure that the diffusion is a very long excursion to the right.
Yeah. So some conditions are missing in my algorithm. And one of these conditions is that you don't leave a box or box of a certain radius or for the 1 over lambda. That is, you don't do a very long excursion.
Sorry, but that is exactly what you, I mean, you don't say anything about time between t and t plus 1 over lambda square. It's not in the algorithm.
No, I mean, in the case of a success, it's okay.
In the case of success, I agree.
And then,
Well, but in the case, but even in the case of success, you have to make sure that diffusion arrive at that wall without making a very big excursion to the right. Or
yeah, we do. You're right. And we do.
Sorry, so you condition that there is no big excursion in between?
I mean, I wonder how you can impose that condition in the algorithm, because you totally forget about I mean, okay, there is a hidden algorithm how to recover the diffusion from your algorithm. But I mean, it is not in the algorithm of origination time. So you create the path with artificial jumps from time to time. And then, you know, the end point of the jump has a right distribution, so to speak. But in order to recover the sample path, you have
I think delta comes from the Aronson bound.
yes, delta comes.
For the diffusion process not leaving the ball. So you don't have to care about big excursion to the right, because diffusion process doesn't leave the ball. And between time 0 and 1 over lambda squared. Okay, so
but then you see, it's okay for the first time, but for the second time,
yeah, okay.
you leave that probability and you push the probability to the second. By the way, do you really actually care what happens between time 0 and 1 over lambda squared?
No.
At least
Have a right distribution at
Yeah.
right time, then
Yes.
you don't.
No, we don't care.
Yeah.
We don't care.
You lose the information, but it's okay.
So just forget about
We lose the information, but it's okay.
Yeah, okay. That I agree.
Okay. Then.
Yeah, I think, no, yeah, yes.
Don't try to reconstruct the diffusion path from your algorithm.
No.
Care about
No. We just care, I mean, I stated the properties of regeneration time saying that the increment in time and position are ID. So that's all I'm looking at. I don't have to, yeah, I don't care about this information that we lost.
okay, I agree. As far as you're talking about the position, I mean, low large numbers for the position, but once you start talking about additive function, you have to care.
Yes, and then we will have to care.
Okay.
Exactly.
Different targets for
Yes, and we modify the algorithm in order to take the additive function into account.
I see.
Okay? So I say for the moment, with this algorithm, we lost that information so that we cannot directly use this algorithm in order to deal with an additive functional, but it's sufficient for the position and time. Okay? Okay. And so, as Yuki was saying, delta, the best value you can choose for delta, it comes from some Aronson bound, and it's okay. I mean, what we get from Aronson bound, because we're using Aronson bound for the process on the scale 1 over lambda and 1 over lambda square, and then we get a delta that does not depend on lambda. So here, in this algorithm, delta does not depend on lambda. And actually, we don't have only one coin tossing. We have a repetition of the coin tossing, and then we use not only one y random variable, but a sequence of them, and they are all distributed with Bldg with the same parameter delta. Okay? So, let us compute two things. That is, what I would like to do is prove that for a fixed lambda, the regeneration time is finite. But in fact, I want more than that. I want to compute the order of magnitude of the first regeneration time. Okay? So how long do we have to keep running the algorithm until we reach this regeneration time to 1 lambda? So there are different things we should do. First, we should run step 1. So step 1, it takes the time of order, the time it takes for the diffusion to proceed of a distance 1 over lambda. But because of lemma 2, the time it takes to reach a distance 1 over lambda is of order 1 over lambda square. So step 1 takes the time of order 1 over lambda square. Okay? And then in lemma 2 we had an exponential decay. So this is, when I say of order 1 over lambda square, it means in a very strong sense that we have an exponential tail with some exponential tail. Then you have this coin tossing thing. So how often do you have to toss a coin in order to get the success? This is 1 over delta. So you toss the coin 1 over delta times. And then there is another step where you ask whether D is finite or infinite. So this is also a coin tossing, so to speak. So we need to know what is the probability that D is infinite, which would actually correspond to a success. That's where we stop. Okay? Now, this is backtracking by a distance 1 over lambda. So the evaluation we had from level 1 is 1 minus exponential minus 1. This is larger than 1 minus exponential minus 1. So this is from lemma 1. Now you can adjust a little bit and decide that this is 1/2, for instance. Instead of 1 over lambda, you choose some other constant. You can fix things. This is just to have light enough notation. And so if you put all these things together, then you see that tau 1 lambda should be of order. So this is of order 1. This is of order 1 over delta, but then you have 1 over lambda square. So something. In terms of lambda, it is of order 1 over lambda square, but this is, if you want to see how it depends on delta, you have to multiply by 1 over delta. Which is good. So this is correct. with some exponential tails. That is, so this is one lemma I stated last time, but if you look at the exponential moment, so some exponential moment of lambda square times tau 1 lambda, then this will be finite, but not only finite, but it's uniformly bounded in terms of lambda, so this will be less than some constant. Okay. For some C1, and some C bar, and all lambda, small enough. That was one bound I stated last time, I guess. And we have a similar statement for the position. So if you look at the position by the natural scale is not lambda square, it's lambda. But if you do something like you can even put the sup for S less than the 1 lambda or XS. So this should be for the 1 over lambda. And you get something like this for the same reason. So in particular, the 1 lambda is finite for a fixed lambda. Now, I write these estimates. I'm not going to use the full strength of these estimates. For the moment, I'm just going to use these estimates for a fixed value of lambda. Now, so you fix lambda, and then you see that tau 1 lambda is finite. Not only it's finite, but it has a finite exponential moment. The position also has a finite exponential moment. And then you write the position of the diffusion. So you write x of t as, so you write x of t as a sum of increments between regeneration times, successive regeneration times. And then you do some error, plus a small error. So you write as many increments as between regeneration times as you can until time t, and then you have something, a little bit of something at the end. This little bit of something at the end, we have many ways to control it. And in the scale of the law of large number, it's not going to contribute. And then you conclude. So conclusion, you prove that Q almost surely, you have this law of large number. That is, if you look at the position at time t divided by t, then this has a limit, and this limit is a deterministic number. So that converges. And we call L of lambda the limit. So this is the law of large numbers for the position. And actually, it's also easy to check from the two lemmas, 1 and 2, that L of lambda is not 0. In particular, L of lambda in the direction E1 is positive. So I want to write one expression. Because not only do we get the law of large numbers, but we get a nice expression of L in terms of regeneration times. So we get that L of lambda can be computed in one regeneration period. So now you have to deal separately with the first regeneration time, because it is only after the first regeneration that what you get is always the same law. That is a law conditioned to the fact that D is infinite. So if you want to have a correct expression, one way to do it is you say that the speed is the mean of the increment between, let's say, the second regeneration time and the first one. And then I should divide by the expected value of time. Let's say 2 lambda minus 2 1 lambda. Or, equivalently, this is the expectation of the position at the first regeneration time, but conditioned on the fact that D is infinite. And then we can do the same thing for time. Conditioned on the fact that D is infinite. Okay. Now we can get more from that, because so we have a powerful way to compare the position of the diffusion with the sum of ID random variables, for which we have all kind of estimates. So we also get from that a CLT. CLT means that if I look at the position x lambda omega 0 at time t in some direction E, and then I subtract what I should, t times L of lambda dot E, divided by square root of t. So this converges in law. So this is convergence in law under P lambda to a centered normal law with a certain variance, sigma lambda. And sigma lambda also has an expression in terms of regenerations. So sigma lambda is the expectation of the square of x. So, sorry, if I fix the direction, then the variance will be sigma lambda evaluated in the direction E. And then I look at x at time to 1 lambda, direction E, minus to 1 lambda, L of lambda dot E squared, and condition on D is infinite, divided by the mean time, the expectation of tau 1 lambda condition on D is infinite. I think this is correct. Okay. Okay.
What you wrote is an expression for the variance. You fix the direction. It's not.
What I wrote is the same thing as here, right? Yes. Correct. Now, maybe I have to choose between two things in 10 minutes. Okay, let me keep the logic of the presentation. So, how to include an additive function? I want to include an additive function of the form the integral from 0 to t, f of omega lambda of s ds. And this, my notation for this is AF evaluated at time t. Okay? So how do we modify the algorithm in order to do that? And you remember that I can be interested in local f's, which can be either bounded or in h-1 infinity. Anyway, I'm assuming that f is local. So it's local with a range RF. So we modify the algorithm, and the trick to include this process is that instead of working with x, we work with z. So this process z, lambda omega of t, this is the R d+1 valued process where the first components are just the components of t. And then, as we did before, we add an extra component which takes into account the additive function. So we'll have an AF of t. And then we add another Brownian motion just to look nice. Then you do no, but it does look nice, no, doesn't it? Then we do the algorithm. So run the algorithm. So except for the fact that we are in RD+1 now, it doesn't change anything. So actually, only one thing changes, because the first step of the algorithm is only about the projection of x in direction E1. So that first step is really unchanged. It doesn't see this extra component. Okay? So the whole thing is, the whole algorithm is not modified, except for one thing, which is the jump at the coin tossing. So when we have a success, when we toss the coin, we jump in a deterministic way, in a deterministic ball, where we choose the next position uniformly at random. But now this ball sits in RD+1. Okay? So things are unchanged. So actually, the algorithm doesn't change, except that you have the ball in RD+1 instead of the ball of RD. But what will be changed is the condition on delta. Okay? Because we need an Aronson bound, but we need an Aronson bound for that process, and the Aronson bound now depends also on the last component. Okay? Except delta. So the new delta depends on Aronson bound for z and not for x. So because z includes f, then delta is a delta f. It depends on f. Okay. And so what happens is that for fixed lambda, and if f is bounded, you have a non-degenerate diffusion process because of the small addition. So you have a delta. But this is if you don't care about the way delta depends on lambda. Okay? Then there exists positive delta that depends on lambda. Now, it does depend on lambda because if you look at the generator, the generator for Z, which we already computed, but you rescale Z, so you put a tilde. This is to rescale it on time scale 1 over lambda square and space scale 1 over lambda. Then you get many things which are very nice, but you get 1 over lambda times the drift part, A dot E1 graph. So that has an extremely bad behavior. Sorry. What you get is 1 over lambda in front of the additive function. So F dy, something like this. Actually, it's an F of omega dot over lambda, something like this. But you get a 1 over lambda here, and which is very bad. But it's okay for a fixed lambda, provided that F is bounded. So this is bounded. So you have an operator in divergence form. I mean, with bounded coefficients. Okay. So that's one case, the first case. And now in the case 2, then in the case 2, that means that F is in H minus 1 infinity. Then you can do better because you can write this term as divergence. So here, instead of this thing, when you look at the generator, so instead of this 1 over lambda, etc., you will get the divergence of F rescaled, F omega. So this is a computation we already did. And then you have an operator in divergence form with coefficients which are bounded, and they are bounded uniformly in lambda. So the Aronson bound is uniform with respect to lambda, and then the choice of delta is uniform. And then we can choose delta independent, so delta is delta F, independent of lambda. Okay? So in the second case, we are in a case which is similar to the situation we had without the additive function, where delta does not depend on lambda, but in the first case, it's not true. Okay? And that's, if you want to explain how delta depends on lambda, then delta also depends on F. So actually, delta F depends on F, so it depends on the range of the support of F, and then it depends on F, that depends depending on the case. So in case 1, it certainly depends on the N-infinite norm of F because of this term. And in case 2, it depends on the N-infinite norm of F omega, this big F. So you optimize, and then you get that it depends on the norm of F, but in H minus 1 infinity. Okay? So if I summarize in terms of estimates for the regeneration times, we'll get regeneration times. So strictly speaking, the regeneration times depend on F, but I'm using the same notation, okay? So let us now call tau lambda, the 1 lambda, the regeneration time for Z. And we want to express the bounds that we can prove, and we will get these two cases. So case 1 will be the case in which we have constants so that we have exponential moments. So we can look at exponential moments of the 1 lambda. Let's say put a C2 to 1 lambda. And we can also get some control on the fluctuation of the path. So you can also look at the sup of the process Z now. Z, I'm going to use Z for the canonical process on RD+1. So the sup before the regeneration time. So you get something like this, being finite. So this is case 1, right? Case 1, that means F is local, always local, but it's bounded. Let me write again, F is always local in the two statements. So you get exponential bounds, but C2 depends on lambda in that case. So here, C2 depends on lambda. So this will be good enough to construct the steady state in the first sense. And then you have case 2. And actually, case 2, the statement is exactly what is still written on the blackboard. That is, you have the same bounds. So here F is in H-1 infinity. And we get exponential modes. But for lambda squared to 1 lambda, and also lambda times the sup. So the sup for S less than 1 lambda of lambda times the norm of D of S. So this is bounded by some constant. And here C2 does not depend on lambda, and also C bar does not depend on lambda. So here, C2 and C bar do not depend on lambda. Okay, do not depend on lambda. So this is true for all small enough lambda. And in fact, in the first case, C2, it depends, let's say, you may choose the same C2 for all F such that the range of locality of F is less than some R1, and you have some control on the L infinite norm. So the L infinite norm is less than 1. Okay? And which, as was mentioned last time, is a property that we use in order to prove that nu lambda is a true probability measure. And also here you have the same property, that is C2, C bar, they are uniform for F's such that you have some control on the radius. Rf is less than some R1. And now we need some control on, I mean, if we assume some control of the norm of F in H-1 infinity. Okay, so this property is used when we construct the steady state in the sense of definition 2 to prove that a steady state has an extension to H tilde minus 1 infinity to non-local functions. Anyway, okay? So I think this is basically where I should stop anyway. But I guess these are okay. I mean, what remains to be done next time is, well, to explicitly write the law of large numbers for additive functionals, but it's almost done. And then what really remains to be done is to send lambda to 0 and see what happens. And so we will definitely use this kind of estimate. Okay? And then, so we will discuss this next time. As a matter of fact, well, when we want to send lambda to 0, there are different ways, these two ways, and one way uses this estimate plus some other estimates, which we already saw. And then there is a second softer way, which will use, in fact, the construction of the regeneration time. So the algorithm that constructs the regeneration times will be, I will use it again. For instance, I will use the solution of the exercise. Something like this. Okay. Do you have any question?
I have one naive question. So you can prove this ELT. Can you further obtain some functional type CLT? But I mean, of course, it's not the usual one because you have to make subtract drift. But so this is for
yeah, I guess. You mean some invariance principle?
Yeah, yeah.
When you take the drift out?
Yes.
Oh, yes, I'm sure we could do that, yes.
How about the local CLT?
This I don't know. I mean, I didn't write it down, really, but I mean, okay. One might hope you at least you have some material to start trying to get some local CLT, right? Because of I mean, we have because we have some bounds on the correct scale. So, okay, I don't know, but there is a chance we could actually get a local version of the CLT.
Regeneration time instead of t, then it's just a sum of IIDs.
Mm-hmm. Yes.
So what you have to do is just only control the last piece.
Mm-hmm. Yes. So the last piece is something of order 1 over lambda square. So you should have some kind of, if you want to prove the local CLT, for instance, you should make sure that this last piece is not going to do something crazy in the time 1 over lambda square. Hmm?
First piece, because the first piece has a different distribution.
Oh, okay. You also have to show that you can neglect the first piece, which is truly of order 1 over lambda square. Okay. So I think you need some a priori bound on how. I mean, if you want to prove the functional CLT or even the CLT, you need some a priori bound on the fact that on a time interval of size 1 over lambda square, the process does not go too far, and actually farther than something of order 1 over lambda. And that, if you only want to know, to get the tightness, I think that this is fine, because we have estimates of this kind, like this, or Aronson, which express that uniformly in lambda, by the time of order 1 over lambda square, you don't go further than distance 1 over lambda, with some exponential things and so on. So that's why I think that the invariance principle should not be a very big issue. And then you get an annealed one, right? So you get this statement, even the central limit theorem, is in the annealed sense,
yes,
right? So I think that just the same you would get the annealed invariance principle. and possibly also the local CLT, but well, I didn't check that, and we okay. I stated, in fact, if we are interested, if you think about the Einstein relation, then the question is, do you have a speed, and can you take the derivative when lambda tends to 0? And in that case, any definition of the speed would do. Is it? I mean, you may ask about the behavior, whether you have a strong law of large numbers and etc. for fixed lambda, for instance. But if you think in terms of the Einstein relation, then I mean, I would be happy, for instance, in the case of a stationary environment, we don't know if we have a law of large numbers. So we don't know if there is an all-motion limit for that. But I would be happy to prove that, for instance, if you take the mean, it converges to something. And that would be, we would take that as a definition for the speed. And then we could ask about the Einstein relation. So, of course, in the case of a stationary environment, we don't know how to prove that even the mean converges. And the same applies to sigma lambda, so at some point, because you may ask, what is the behavior of sigma lambda when lambda tends to 0? But if you just want to raise the question, then the central limit theorem is enough to define sigma lambda. Actually, the invariance principle is not needed to define sigma lambda, although it should be true. Okay. Any other question?
Thank you.
Thank you.